Mars turns in its ancient rhythm, one rotation every 24 hours and 37 minutes, just slightly out of step with Earth's familiar cadence. The planet exhales thin streams of carbon dioxide into the void, while its rust-coloured surface catches the distant warmth of a sun that appears half the size it does from our home world. In the pre-dawn darkness of a Martian morning, something unprecedented approaches through the cold vacuum between worlds. The comet designated 3/Atlas moves along its hyperbolic path with the patient inevitability of celestial mechanics. It carries within its nucleus the frozen chemistry of the outer solar system, water ice mixed with carbon monoxide, methane, and ammonia that condensed in temperatures barely above absolute zero. For millions of years, this wandering archive has preserved the molecular signatures of an epoch when the planets were still forming. When Jupiter's gravity carved the asteroid belt into its current scattered arrangement, when the solar wind first began its eternal outward rush, scientists on Earth detect 3/Atlas through careful observations of its brightening tail, a gossamer stream of sublimating gases and liberated dust particles that extends millions of kilometers behind the comet's nucleus. The tail points always away from the sun, sculpted by solar radiation pressure and the steady flow of charged particles that stream outward from our star. Through telescopes, astronomers measure the comet's trajectory with increasing precision, calculating that its path will carry it through the outer reaches of Mars's tenuous atmosphere. Mars possesses no significant magnetic field to deflect this interstellar matter. Billions of years ago, the planet's molten iron core generated protective magnetic boundaries that shielded its early, thicker atmosphere from solar erosion. But as Mars cooled and its internal dynamo failed, the magnetic field collapsed, leaving the planet's gaseous envelope exposed to the relentless stripping action of solar wind. What remains now measures less than 1% the density of Earth's atmosphere at sea level. The approaching encounter unfolds with a kind of geological patience that renders human timescales nearly irrelevant. 3/Atlas has travelled for millennia to reach this moment of intersection, carrying pristine samples of material that formed in the frigid darkness beyond Neptune's orbit. The comet's nucleus, perhaps 10 kilometres across, rotates slowly as it approaches, each revolution exposing different regions of ancient ice to solar heating. Instruments aboard Mars orbiters begin detecting the first microscopic signatures of the comet's presence. Spectrometers sensitive to trace atmospheric constituents register subtle increases in water vapour and carbon monoxide concentrations in Mars's upper atmosphere. These molecules arrive as individual immigrants from interstellar space, each one carrying the chemical fingerprint of processes that occurred when the solar system was young. The dance between celestial visitor and planetary host proceeds according to laws discovered by Kepler and refined by Newton. Yet the specific details of atmospheric interaction remain largely mysterious to scientists. How efficiently do comet particles transfer their momentum to atmospheric molecules? What chemical reactions occur when pristine outer solar system materials encounter the oxidized chemistry of Mars? How long do these foreign molecules persist in the planet's thin envelope before escaping to space or settling to the surface? Mars's atmosphere extends upward through distinct layers, each defined by temperature gradients and molecular composition. The troposphere, where dust storms rage and clouds occasionally form, reaches about 60 kilometers altitude. Above this lies the stratosphere, where temperatures increase with height due to absorption of solar ultraviolet radiation. Higher still, the thermosphere and exosphere mark the gradual transition from planetary atmosphere to interplanetary space. It is in these uppermost atmospheric regions that 3I/Atlas will leave its gentlest footprint. The comet's tail extends far beyond the orbit of Mars, creating a diffuse cloud of particles and gases that the planet will swim through for several days. Most of this material consists of microscopic dust grains and individual molecules, moving at speeds determined by solar radiation pressure and the comet's own outgassing velocity. Ground-based telescopes track the comet's approach with patient precision, recording subtle changes in its brightness and spectral characteristics. The nucleus rotates with a period of several hours, causing periodic variations in the intensity of gas and dust emission. Solar heating drives sublimation on the sun-facing hemisphere while the shadowed regions remain frozen, creating complex patterns of outflow that sculpt the developing tail. Mars orbits the Sun at an average distance of 228 million kilometers, following an elliptical path that brings it as close as 207 million kilometers during perihelion and carries it as far as 249 million kilometers at aphelion. The planet's thin atmosphere responds sensitively to these orbital variations, expanding and contracting with seasonal changes in solar heating. During the approach of 3I/Atlas, Mars travels through the portion of its orbit where atmospheric density reaches near minimum values. The encounter promises to unfold with exquisite subtlety. Unlike the dramatic impact events that have occasionally punctuated planetary evolution, this interstellar visitation will leave only the faintest trace of its occurrence. No craters will mark the surface. No massive atmospheric disturbances will reshape weather patterns. Instead, the interaction will manifest as a gentle chemical whisper, detectable only through sophisticated spectroscopic analysis and atmospheric modelling. Scientists calculate that the total mass of comet material intercepted by Mars's atmosphere will measure in mere kilograms, distributed over millions of cubic kilometers of near-vacuum space. Each individual dust grain carries kinetic energy proportional to its tiny mass and considerable velocity, but the collective effect resembles a soft rain of cosmic debris rather than any form of bombardment. The approach continues through the patient darkness of interplanetary space, where temperature barely rises above the cosmic microwave background radiation that permeates the universe. 3I/Atlas has spent most of its existence in this profound cold, preserving molecular structures and isotopic ratios that record conditions from the solar system's formation. Now, as it ventures closer to the Sun than it has ever travelled, solar heating begins to awaken the comet's frozen chemistry. Mars waits in its orbital path with the timeless patience that characterizes all planetary motion. The red planet has witnessed the passage of countless smaller visitors over its 4 billion-year history, accumulating a steady background influx of interplanetary dust and meteoritic material. But the approaching encounter with 3I/Atlas represents something qualitatively different. A direct atmospheric interaction with pristine material from the outer solar system, carrying chemical signatures that may illuminate processes from the epoch of planetary formation. The stage is set for an encounter that will unfold over the coming days with the measured cadence of celestial mechanics, leaving Mars's thin atmosphere briefly enriched with ancient chemistry from the cold darkness beyond Neptune's realm. The visitor from beyond Neptune carries within its frozen heart the undisturbed chemistry of the outer solar system's birth. 3I/Atlas formed in the primordial disk of gas and dust that surrounded the young Sun 4.5 billion years ago. When temperatures in the outermost regions barely exceeded absolute zero, and volatile compounds could condense into solid grains. Unlike the rocky materials that built the inner planets, this comet nucleus preserves water ice, carbon monoxide, methane, and ammonia in proportions that reflect the original composition of the solar nebula. Scientists studying the comet's spectral signatures detect the characteristic absorption lines of these ancient ices, each molecular species revealing itself through the specific wavelengths of light it absorbs as solar radiation passes through the expanding coma. Water vapor produces its familiar fingerprint in the infrared spectrum, while carbon monoxide appears as sharp lines in the ultraviolet. These molecules sublimate directly from solid to gas as solar heating penetrates the comet's dark, carbonaceous surface, bypassing the liquid phase entirely in the vacuum of space. The nucleus of 3Atlas rotates with a period of 8 hours and 14 minutes, causing periodic variations in gas production as different regions experience sunrise and sunset. Thermal imaging reveals temperature differences across the surface that correlate with the comet's complex topography. Deep craters and steep ridges cast shadows that preserve patches of primordial ice, even during peak solar heating. These temperature gradients drive convective flows within the thin coma that surrounds the nucleus, creating subtle density variations detectable through careful, photometric analysis. Mars approaches this expanding cloud of ancient chemistry with its own unique atmospheric signature. The planet's thin envelope consists primarily of carbon dioxide, with trace amounts of nitrogen, argon, oxygen, carbon monoxide, and water vapor. The relative abundance of these constituents varies with altitude, season, and local weather patterns, creating a dynamic chemical environment that will soon encounter molecular visitors from the solar system's formation epoch. The gravitational influence between Mars and 3Atlas remains negligible throughout their encounter. The comet's trajectory follows a nearly perfect hyperbola, curved only slightly by the Sun's gravitational field and unperturbed by the relatively tiny mass of Mars. This geometric precision means the encounter unfolds according to predictable celestial mechanics, allowing scientists to calculate exactly when and where the planet's atmosphere will intercept particles from the comet's tail. Instruments aboard NASA's MAVEN orbiter and ESA's Mars Express begin detecting the first molecular signatures of the approaching visitor. Mass spectrometers designed to analyze atmospheric composition register minute increases in water vapor concentration at altitudes above 200 kilometers. These individual molecules arrive as the outermost envelope of 3Atlas's expanding coma encounters Mars's exosphere, where atmospheric density has dropped to levels comparable to the best laboratory vacuum chambers on Earth. The interaction proceeds with extraordinary gentleness. Each water molecule from the comet carries kinetic energy, determined by its thermal velocity and the expansion speed of the coma, typically several hundred meters per second. When these molecules collide with components of Mars's upper atmosphere, they transfer momentum and energy through elastic scattering events that occur billions of times per second across millions of cubic kilometers of near vacuum space. Chemical reactions between comet-derived molecules and atmospheric constituents remain largely theoretical, limited by the extremely low densities at interaction altitudes. However, laboratory studies suggest that water molecules from 3Atlas might participate in ion-molecule reactions with carbon dioxide ions produced by solar ultraviolet radiation in Mars's ionosphere. These processes could temporarily alter the chemical balance of the upper atmosphere, creating short-lived molecular species detectable through high-resolution spectroscopy. The comet's dust component presents its own scientific mysteries. Microscopic grains composed of silicate minerals, organic compounds, and refractory carbon particles follow ballistic trajectories after escaping the nucleus's weak gravitational field. Solar radiation pressure accelerates the smallest particles away from the Sun, while larger grains maintain courses closer to the comet's orbital path. This size-dependent sorting effect means that Mars encounters different populations of dust particles depending on the planet's position relative to the comet and Sun. Atmospheric drag begins affecting comet particles at altitudes near 150 kilometers, where Mars's thermosphere reaches its maximum density. Individual dust grains experience deceleration proportional to their cross-sectional area and inversely proportional to their mass, causing them to spiral inward through the atmospheric layers. The largest particles might survive this descent to reach the surface, while smaller grains undergo complete vaporization due to frictional heating during atmospheric entry. Ground-based observatories track subtle changes in 3I/Atlas's brightness and spectral characteristics as the comet approaches perihelion. Photometric measurements reveal periodic fluctuations with amplitudes of several percent, indicating heterogeneous composition across the nucleus surface. Some regions appear enriched in volatile ices that sublimate readily under solar heating, while others consist primarily of refractory materials that remain stable at higher temperatures. The comet's orbital mechanics follow principles established by Johannes Kepler 4 centuries ago. Yet modern computational techniques reveal subtle perturbations caused by non-gravitational forces. Asymmetric outgassing creates small but measurable changes in 3I/Atlas's trajectory, as escaping gases generate tiny rocket-like thrust forces that accelerate the nucleus in directions determined by its rotation axis and surface topography. These perturbations accumulate over multiple orbits, making long-term prediction of comet positions a challenging exercise in celestial mechanics. Mars's magnetic field, or rather its conspicuous absence, plays a crucial role in the approaching encounter. Unlike Earth's protective magnetosphere, which deflects most solar wind particles and cosmic rays, Mars lacks significant magnetic boundaries to shield its atmosphere from direct interaction with interplanetary material. Solar wind ions regularly penetrate to altitudes below 200 kilometers, where they participate in charge exchange reactions and contribute to atmospheric escape processes that have gradually stripped away much of the planet's original gaseous envelope. This magnetic vulnerability means that particles from 3I/Atlas can penetrate directly into Mars's upper atmosphere without encountering the magnetic barriers that would deflect them around Earth. The interaction occurs in a regime where atmospheric molecules exist as both neutrals and ions, creating complex chemical networks that involve electron impact ionization, radiative recombination, and dissociative electron attachment. Temperature profiles through Mars's atmospheric layers reveal the thermal environment that will greet molecules from the approaching comet. The thermosphere, extending from about 100 to 200 kilometers altitude, experiences extreme temperature variations that depend on solar activity and local time. During periods of high solar flux, temperatures can exceed 200 degrees Celsius, while minimum values during polar winter approach minus 150 degrees Celsius. These temperature extremes affect the chemical reactivity and residence time of comet-derived molecules in Mars's atmosphere. Water molecules from 3I/Atlas encounter thermal conditions ranging from near freezing in the lower thermosphere to several hundred degrees in regions of peak solar heating. Such temperature variations drive complex photochemical networks that convert simple molecules into more complex species through sequences of reactions involving atomic oxygen, hydrogen, and carbon-bearing radicals. The scientific value of the approaching encounter extends beyond its immediate atmospheric effects. 3I/Atlas represents a natural experiment in interplanetary chemistry, providing researchers with an opportunity to study how pristine outer solar system materials interact with the oxidized environment of Mars's atmosphere. The event offers insights into processes that may have been more common during the early solar system. when comet bombardment rates exceeded current levels by orders of magnitude. Theoretical models suggest that ancient Mars experienced frequent encounters with comets and asteroids that delivered significant quantities of water, organic compounds, and other volatile materials to the planet's surface and atmosphere. The interaction with 3/Atlas provides a scaled-down version of these ancient processes, allowing scientists to test atmospheric chemistry models and refine understanding of how extraterrestrial materials influence planetary evolution during the solar system's turbulent youth. Mars breathes through its tenuous upper atmosphere with a rhythm measured in centuries rather than seconds. The planet's gaseous envelope extends upward from the surface in layers so thin that a single cubic meter of air at 100 kilometers altitude contains fewer molecules than the same volume at Earth's sea level holds in a single breath. Yet, within this near vacuum, sophisticated instruments detect the first whispered signatures of 3/Atlas's approach, as individual molecules from the comet's expanding coma drift into the outermost reaches of the Martian atmosphere. The detection begins at altitudes where the boundary between atmosphere and interplanetary space becomes a matter of definition rather than physical reality. At 400 kilometers above Mars's surface, atmospheric density has decreased to levels where molecules travel vast distances between collisions, following ballistic trajectories that arc through the planet's gravitational field like microscopic satellites. Here, in the exosphere, the first water molecules sublimated from 3/Atlas's ancient ice begin their interaction with Mars's sparse collection of atmospheric constituents. Mass spectrometers aboard orbiting spacecraft register these arrivals as subtle increases in water vapor concentration. Measurements so delicate they require sophisticated statistical analysis to distinguish genuine signals from instrumental noise. Each detected molecule represents a triumph of technological precision instruments designed to count individual atomic and molecular species in environments where matter exists at densities millions of times lower than the best laboratory vacuums achieved on Earth. The interaction unfolds according to kinetic theory principles established in the 19th century. Yet the specific details involve quantum mechanical processes that remain active areas of research. When a water molecule from 3/Atlas collides with a carbon dioxide molecule from Mars's atmosphere, the encounter proceeds through potential energy surfaces calculated using computational quantum chemistry. The collision might result in elastic scattering, where both molecules retain their chemical identity while exchanging kinetic energy, or inelastic processes that transfer energy between rotational and vibrational quantum states. Scientists monitoring atmospheric composition through remote sensing techniques observe variations that correlate with 3/Atlas's approach trajectory. Infrared spectrometers detect subtle shifts in the absorption signatures of water vapor and carbon monoxide at specific altitudes, indicating enhanced concentrations of these molecules in regions where the comet's coma intersects Mars's upper atmosphere. The signals require careful calibration to account for instrumental drift, atmospheric temperature variations, and contamination from other sources. Temperature measurements reveal the thermal environment where these molecular encounters occur. Mars's thermosphere experiences dramatic heating during periods of high solar activity, when ultraviolet and X-ray radiation from the Sun deposit energy through photoionization and photodissociation processes. During quiet solar conditions, temperatures can drop below -100 degrees Celsius, creating a frigid environment where chemical reaction rates decrease exponentially according to Arrhenius kinetics. The planet's atmospheric circulation patterns add complexity to the interaction dynamics. Global-scale winds in Mars's upper atmosphere transport trace constituents across vast distances, mixing comet-derived molecules with indigenous atmospheric components in ways that depend on seasonal variations and hemispheric asymmetries. These circulation cells operate on timescales of weeks to months, much longer than the brief period of 3 Atlas's closest approach, but still rapid enough to redistribute comet material before it can settle to lower altitudes. Photochemical networks in Mars's upper atmosphere involve dozens of molecular species connected through hundreds of chemical reactions, each proceeding at rates determined by temperature, pressure, and solar radiation intensity. The arrival of water molecules from 3Atlas introduces new pathways for hydrogen chemistry, potentially altering the production and destruction rates of hydroxyl radicals, hydrogen peroxide, and other reactive species that play important roles in atmospheric photochemistry. Laboratory studies conducted in Earth-based vacuum chambers provide insight into the fundamental collision processes occurring in Mars's upper atmosphere. Researchers use molecular beam techniques to study how water molecules interact with carbon dioxide under conditions that simulate the low-density, high-velocity environment at 200 km altitude. These experiments reveal that collision cross-sections depend sensitively on the relative kinetic energies and internal quantum states of the colliding molecules. The gravitational influence of Mars subtly affects the trajectories of particles in 3Atlas's coma through three-body dynamics involving the comet nucleus, individual dust grains or molecules, and the planet itself. While Mars's gravitational field cannot significantly deflect the comet's hyperbolic trajectory, it does focus particles from the coma toward the planet's night-side hemisphere, creating spatial variations in the atmospheric interaction intensity. Magnetic field measurements from Mars orbiters reveal the complex electromagnetic environment where comet particles encounter the planet's ionosphere. Although Mars lacks a global magnetic field, localized magnetic anomalies in the planet's crust create miniature magnetospheres that can deflect charged particles and influence plasma dynamics in the upper atmosphere. These crustal magnetic fields interact with the solar wind to form current sheets and magnetic reconnection regions that accelerate ions and electrons to high energies. The isotopic composition of water molecules from 3Atlas carries information about conditions in the outer solar system during the epoch of planetary formation. Deuterium to hydrogen ratios in comet ice reflect the temperature and chemical environment where the water molecules originally condensed, providing constraints on models of solar nebula evolution. When these ancient water molecules mix with atmospheric water vapor on Mars, they create isotopic signatures detectable through high-resolution spectroscopy. Atmospheric escape processes continuously remove gas from Mars's upper atmosphere, carrying away molecules through several distinct mechanisms. Thermal escape allows the lightest atoms and molecules to achieve velocities exceeding the planet's gravitational escape speed, while sputtering by solar wind ions ejects heavier species through momentum transfer. The temporary enhancement of atmospheric density caused by 3Atlas might slightly increase escape rates, though the effect remains too small for direct measurement with current instrumentation. Dust grains from the comet's tail follow different trajectories than gas molecules due to their higher mass-to-charge ratios and sensitivity to radiation pressure forces. The smallest particles, with diameters measured in nanometers, experience significant acceleration by solar photons and may never reach Mars's atmosphere. Intermediate-sized grains encounter atmospheric drag at altitudes near 120 kilometers, where frictional heating causes sublimation of volatile components and gradual erosion of refractory cores. Computational models of the interaction require sophisticated numerical techniques to handle the wide range of spatial and temporal scales involved. Molecular dynamics simulations track individual particle trajectories through Mars's gravitational field, while fluid dynamics models describe bulk atmospheric properties using average quantities. The coupling between these different computational approaches remains an active area of research in atmospheric physics. Ground-based telescopic observations provide complementary data on three I/Atlas's gas production rates and dust emission patterns as the comet approaches perihelion. Narrowband photometry isolates emission from specific molecular species, revealing periodic variations that correlate with the nucleus rotation period. These measurements help constrain models of comet outgassing and improve predictions of particle flux densities in the vicinity of Mars. The encounter represents a natural laboratory for studying collision processes that occur throughout the solar system wherever cometary material interacts with planetary atmospheres. Similar interactions have shaped the chemical evolution of atmospheres on Venus, Earth, Jupiter's moons, and Saturn's satellite Titan, though each environment presents unique physical and chemical conditions that modify the fundamental collision dynamics. Scientific instruments designed for atmospheric research operate at the limits of their sensitivity to detect signals from the three I/Atlas encounter. Photomultiplier tubes convert individual photons into measurable electrical pulses, while charge-coupled device arrays integrate photon counts over precisely timed intervals. The statistical nature of these measurements requires careful analysis to distinguish genuine signals from random fluctuations in detector response. Dancing with gravity's edge, 3I/Atlas follows its hyperbolic trajectory with the mathematical precision of celestial mechanics. The comet neither slows for capture nor accelerates toward escape, it simply passes through, tracing a path determined by its initial velocity vector and the Sun's gravitational influence. This geometric perfection means the encounter with Mars unfolds according to predictable orbital dynamics, yet the specific atmospheric interactions remain delicately poised between order and chaos. The mathematics governing hyperbolic orbits date to Isaac Newton's Principia, where inverse square gravitational forces produce conic section trajectories depending on a body's total energy. Objects with negative total energy follow closed elliptical paths, while those with positive energy trace open hyperbolas that extend to infinity. 3I/Atlas possesses precisely the energy balance that carries it through the inner solar system on a one-time visit, never to return along the same path. Mars's gravitational field exerts minimal influence on the comet's overall trajectory, creating perturbations measured in kilometers rather than the astronomical units that separate planets. Yet this tiny deflection focuses particles from the comet's coma toward Mars's night-side hemisphere, where atmospheric densities reach their daily minimum values. The geometric alignment creates a natural experiment in rarefied gas dynamics. As comet molecules encounter an atmospheric environment operating at the boundary between continuum fluid behavior and molecular kinetic regimes, orbital mechanics calculations reveal that 3I/Atlas approaches Mars at a relative velocity of 22.7 km per second, fast enough to traverse the planet's diameter in under 5 minutes, yet slow enough for meaningful atmospheric interaction. This velocity represents the vector sum of the comet's heliocentric motion and Mars's orbital velocity, modified by gravitational focusing effects that become significant only within the planet's sphere of influence. The encounter geometry creates distinct phases of interaction as different portions of 3I/Atlas's extended coma pass through Mars's atmospheric layers. Initially, only the most diffuse outer envelope of the comet's gas cloud intersects the planet's exosphere, producing subtle enhancements in atmospheric density detectable only through sensitive spectroscopic analysis. As the comet's trajectory carries denser regions of the coma closer to Mars, the atmospheric response intensifies proportionally. Scientists modelling the interaction face computational challenges that arise from the vast range of spatial scales involved. Individual molecules in the comet's coma travel distances measured in planetary radii between collisions, while atmospheric turbulence in Mars's lower thermosphere operates on scales of kilometres. Bridging these disparate regimes requires hybrid simulation approaches that combine molecular dynamics techniques with fluid mechanics approximations. The comet's rotation period of 8.23 hours creates periodic variations in gas production that propagate through the coma at velocities determined by thermal expansion and radiation pressure effects. Mars encounters this structured outflow pattern as the planet moves through different cross-sections of the rotating gas cloud, experiencing temporal variations in molecular flux that correlate with 3I/Atlas's spin state, rather than any intrinsic atmospheric dynamics. Gravitational focusing by Mars concentrates comet particles into a roughly conical volume downstream from the planet's orbital position, creating enhanced particle densities in regions where the atmospheric interaction occurs most intensely. The focusing effect depends on particle mass and velocity, with heavier dust grains experiencing stronger gravitational deflection than lighter gas molecules. This mass-dependent sorting produces spatial variations in composition throughout the interaction region. Solar radiation pressure acts as a persistent force opposing gravitational attraction for particles in 3I/Atlas's coma, with the relative importance of these competing effects determined by particle size and composition. Submicron dust grains experience radiation pressure forces that can exceed gravitational attraction, causing them to follow trajectories that curve away from the Sun regardless of planetary gravitational fields. Larger particles follow nearly ballistic paths modified by weak radiation pressure perturbations. The approaching encounter unfolds in a reference frame, where Mars appears nearly stationary, while 3V/Atlas streams past at hyperbolic velocity. From the comet's perspective, Mars represents a minor gravitational anomaly that briefly perturbs particle trajectories before fading into the background of interplanetary space. The interaction duration depends on the spatial extent of atmospheric effects rather than gravitational capture times, lasting several days as the extended coma envelope traverses the planet's sphere of influence. Temperature variations throughout Mars's upper atmosphere create thermal gradients that drive atmospheric circulation on scales comparable to the planet's radius. These large-scale motions transport comet-derived molecules horizontally across hemispheres, while vertical mixing carries exotic chemistry downward toward denser atmospheric layers. The circulation timescales, measured in weeks, exceed the brief encounter duration but remain fast enough to redistribute comet material before gravitational settling can concentrate it at specific altitudes. Atmospheric drag forces acting on comet particles produce heating effects that depend on particle size, composition, and entry velocity. The smallest grains undergo complete vaporization while traversing Mars's thermosphere, contributing their constituent atoms directly to atmospheric chemistry networks. Intermediate-sized particles experience partial ablation that strips away volatile components while leaving refractory cores to continue downward trajectories toward the planet's surface. The hyperbolic trajectory of 3I/Atlas ensures that gravitational binding never occurs. The comet's kinetic energy per unit mass exceeds the gravitational potential energy throughout the encounter. This energy balance means that particles escaping from the comet's nucleus retain sufficient velocity to escape Mars's gravitational field, unless they undergo multiple collisions with atmospheric molecules that gradually dissipate their kinetic energy through thermalization processes. Perturbation theory techniques allow scientists to calculate how Mars's gravitational field modifies particle trajectories within 3y/8-Lass's coma, without requiring full numerical integration of the equations of motion. These analytical approximations reveal that particle deflections remain small compared to typical collision mean free paths in the upper atmosphere, indicating that gravitational focusing effects do not significantly alter collision dynamics or chemical reaction rates. The encounter represents a singular event in Mars's atmospheric history. Never before have ground-based instruments possessed sufficient sensitivity to detect the passage of an individual comet through the planet's upper atmosphere. Previous interactions undoubtedly occurred throughout geological time, but their signatures remained below the detection threshold of earlier observational techniques. Modern spectroscopic capabilities finally enable direct study of these ephemeral encounters. The chemistry of ancient ice awakens as 3I/Atlas ventures closer to the Sun than any point in its multi-million-year journey through interstellar space. Solar heating penetrates the comet's dark surface, driving sublimation processes that transform solid phases directly into vapor without passing through liquid intermediates. Water ice, frozen for eons at temperatures near absolute zero, begins its transition to gas as photons deliver energy sufficient to break the hydrogen bonds that hold crystalline structures together. Carbon monoxide ice sublimes at temperatures far below water's transition point, creating the first gaseous emissions as 3y/Atlas approaches the inner solar system. This simple molecule, consisting of carbon and oxygen atoms joined by a triple bond, carries within its structure the chemical signature of stellar nucleosynthesis processes that created heavy elements in the cores of ancient stars. The carbon monoxide now streaming from the comet's nucleus formed in stellar interiors billions of years before the solar system existed. Recycled through multiple generations of stellar birth and death, methane ice contributes its own spectral signature to the expanding coma, producing characteristic absorption lines in the near-infrared spectrum that ground-based telescopes detect with increasing intensity as solar heating accelerates sublimation rates. Each methane molecule represents a tetrahedral arrangement of one carbon atom surrounded by 4 hydrogen atoms, a geometric configuration that remains stable across the extreme temperature ranges encountered in interplanetary space. The isotopic ratios preserved within these ancient ices provide clues about conditions during the solar system's formation epoch. Deuterium-enriched water molecules in comet ice record the low-temperature chemistry that occurred in the outer regions of the solar nebula, where hydrogen isotope fractionation processes favoured incorporation of the heavier deuterium nucleus over ordinary hydrogen. These isotopic signatures remain frozen in time, unaltered by billions of years of storage in the cold vacuum beyond Neptune's orbit. Ammonia ice begins subliming at slightly higher temperatures than carbon monoxide, adding nitrogen-bearing molecules to the comet's outgassing inventory. The ammonia molecule's pyramidal structure, with 3 hydrogen atoms bonded to a central nitrogen, creates distinctive spectroscopic features that reveal the presence of this primordial ice component. Ammonia's chemical reactivity in aqueous solutions has led some researchers to speculate about its role in prebiotic chemistry, though such reactions remain impossible in the vacuum environment of interplanetary space. Mars's atmosphere, dominated by carbon dioxide with trace amounts of nitrogen, argon, and water vapor, presents a unique chemical environment for interaction with these comet-derived molecules. The planet's oxidizing atmospheric chemistry contrasts sharply with the reducing conditions where 3I/8-Lass's ices originally formed. creating opportunities for redox reactions that might not occur in other planetary environments within the solar system. Chemical kinetics theory predicts that most gas phase reactions between comet molecules and atmospheric constituents will proceed slowly at the low temperatures and pressures characteristic of Mars's upper atmosphere. Activation energy barriers that must be overcome for chemical bonds to break and reform typically require thermal energies corresponding to temperatures of hundreds or thousands of degrees. The frigid conditions at 150-kilometer altitude, where atmospheric temperatures rarely exceed -50 degrees Celsius, severely limit the rates of most chemical transformations. However, photochemical processes driven by solar ultraviolet radiation can bypass these thermal limitations by providing energy directly to specific molecular bonds. Ultraviolet photons with wavelengths shorter than 200 nanometers carry sufficient energy to dissociate water molecules into hydrogen and hydroxyl radicals, initiating chemical cascades that produce more complex species through subsequent radical reactions. These photodissociation processes operate efficiently even at the low temperatures characteristic of planetary upper atmospheres. Ion-molecule reactions proceed much more rapidly than neutral-neutral interactions due to the strong electrostatic forces between charged and uncharged species. Mars's ionosphere contains significant concentrations of carbon dioxide ions produced by solar extreme ultraviolet radiation, creating opportunities for rapid chemical processing of water molecules from 3/Atlas through proton transfer and charge exchange mechanisms. These ionic processes can occur on collision timescales, limited only by the rate at which reactants encounter each other in the low-density upper atmospheric environment. Laboratory measurements of reaction rate coefficients provide quantitative data for modelling chemical transformations in Mars's upper atmosphere. Though extrapolating these results to planetary conditions requires careful consideration of temperature and pressure dependencies, most laboratory studies are conducted at much higher pressures than those characteristic of planetary atmospheres, necessitating theoretical corrections based on collision theory and transition state calculations. The temporal evolution of chemical composition following the 3/Atlas encounter depends on the balance between production and loss processes for each molecular species. Water molecules injected into Mars's atmosphere undergo photodissociation on timescales of days to weeks, depending on solar flux intensity and atmospheric optical depth. The resulting hydrogen atoms escape to space through thermal and non-thermal mechanisms, while hydroxyl radicals participate in catalytic cycles that influence the atmospheric oxygen budget. Atmospheric mixing processes transport chemically processed molecules, both horizontally and vertically through Mars's upper atmosphere, distributing comet-derived chemistry across spatial scales much larger than the immediate interaction region. Global circulation patterns driven by solar heating and planetary rotation create transport timescales that range from days for zonal mixing to some months for a meridional circulation, ensuring that chemical signatures of the encounter spread throughout the atmospheric system. Heterogeneous chemistry occurring on atmospheric aerosol particles might provide additional pathways for chemical processing of comet-derived molecules, though the low concentrations of condensed phases in Mars's upper atmosphere limit the importance of these surface-catalyzed reactions. Dust storms occasionally loft particles to altitudes exceeding 50 kilometers, but the interaction altitude of 100-200 kilometers typically contains negligible concentrations of solid or liquid particles. The chemical complexity of 3/Atlas's outgassing inventory extends far beyond the simple molecules detectable through ground-based spectroscopy. Organic compounds containing carbon-hydrogen bonds, sulfur-bearing species, and complex hydrocarbons likely contribute to the comet's chemical emission, but remain below current detection limits. These minor constituents might participate in exotic chemical networks that produce trace species detectable only through the most sensitive analytical techniques. Mass spectrometric measurements aboard Mars orbiters provide direct chemical analysis of atmospheric composition at the altitudes where comet interaction occurs, offering unprecedented insights into the molecular level details of the encounter. These instruments can detect individual atomic and molecular species at concentration levels of parts per trillion, revealing subtle chemical perturbations that would remain invisible to remote sensing techniques. Magnetosphere memories linger in the crustal rocks of Mars, remnants of a planetary magnetic field that died billions of years ago when the planet's molten iron core cooled and solidified, unlike Earth's robust magnetosphere, which deflects solar wind particles and cosmic rays through its dipolar magnetic field, extending tens of thousands of kilometers into space. Mars presents no such protective barrier to the approaching chemistry of 3Y/Atlas. The comet's molecular emigrants encounter a planet magnetically naked, its atmosphere directly exposed to the interplanetary medium. The absence of a global magnetic field fundamentally alters how comet particles interact with Mars's upper atmosphere. On Earth, incoming charged particles spiral along magnetic field lines, often deflected around the planet entirely or channeled into polar regions where they create auroral displays. Mars offers no such electromagnetic choreography, solar wind ions, cosmic rays, and now molecules from 3/Atlas penetrate directly into atmospheric layers without magnetic interference or deflection. Localized magnetic anomalies scattered across Mars's southern hemisphere provide the only remnants of the planet's magnetic past. These crustal magnetization patterns, detected by orbiting spacecraft, create miniature magnetospheres extending perhaps a few hundred kilometers above the surface, too weak and too localized to provide global atmospheric protection. These magnetic patches nonetheless create complex plasma physics environments where charged particles undergo acceleration, heating, and chemical modification through electromagnetic processes. The solar wind, a continuous stream of charged particles flowing outward from the Sun at velocities approaching 400 kilometers per second, encounters Mars's unshielded atmosphere with a direct impact. Protons and alpha particles in the solar wind carry kinetic energies sufficient to displace atmospheric molecules through momentum transfer, gradually stripping away the planet's gaseous envelope through a process known as atmospheric sputtering. This erosive mechanism has operated for billions of years, reducing Mars's atmospheric pressure to its current tenuous state. Maven's spacecraft measurements reveal the detailed structure of Mars's ionosphere, where solar ultraviolet radiation ionizes atmospheric molecules to create a plasma environment containing roughly equal numbers of positive ions and free electrons. The ionosphere extends from about 100 to 300 kilometers altitude, overlapping precisely with the region where particles from 3Y/Atlas will interact most intensively with atmospheric constituents. This plasma environment facilitates rapid charge exchange reactions between comet molecules and atmospheric ions. Magnetic reconnection events occur sporadically in the wake region behind Mars, where the planet's interaction with the solar wind creates current sheets and magnetic field discontinuities. These electromagnetic phenomena accelerate particles to high energies through processes analogous to those operating in Earth's magnetotail. Though the spatial scales and energy budgets involved remain much smaller due to Mars's weak magnetic environment, reconnection events might temporarily enhance atmospheric escape rates during periods of high solar wind dynamic pressure. The interplanetary magnetic field embedded in the solar wind drapes around Mars like a curtain, creating induced magnetospheric boundaries that partially shield the planet's atmosphere from direct solar wind impact. This draped field configuration changes continuously as the interplanetary magnetic field rotates with solar wind fluctuations, creating time-variable electromagnetic environments that influence atmospheric chemistry through field-aligned currents and plasma wave generation. Charged particles in 3/8 ionized coma respond to electromagnetic fields through gyration about magnetic field lines, with characteristic frequencies determined by particle mass and charge. Protons gyrate at frequencies near 1,500 Hz in typical interplanetary magnetic field strengths, while heavier molecular ions exhibit proportionally lower gyro frequencies. These cyclotron motions create spiral trajectories that can transport charged comet material across magnetic field lines through gradient and curvature drift mechanisms. Plasma instabilities develop when charged particle populations possess different temperatures or drift velocities relative to background magnetic fields, generating electromagnetic waves that can accelerate particles and modify chemical reaction rates through wave-particle interactions. The injection of comet-derived ions into Mars's magnetosphere might trigger such instabilities, creating transient electromagnetic phenomena detectable by sensitive magnetometers aboard orbiting spacecraft. The Hall effect, arising from the curved trajectories of charged particles in magnetic fields, generates electric fields perpendicular to both magnetic field and particle motion directions. These electric fields drive plasma convection and create charge separation that influences chemical reaction pathways through electrostatic acceleration of reactant species. The Hall effect operates most efficiently in partially ionized plasmas where ion and electron motion become decoupled. Atmospheric escape from Mars occurs through several electromagnetic mechanisms that depend on the planet's magnetic environment. Polar wind acceleration occurs where magnetic field lines connect directly to interplanetary space, allowing atmospheric ions to stream away from the planet along field-aligned trajectories. Pickup ion acceleration occurs when newly created atmospheric ions encounter the convecting solar wind plasma and become swept away from the planet through electromagnetic forces. Dust grains in 3I/Atlas's coma acquire electric charges through photoemission and plasma interactions, becoming sensitive to electromagnetic forces despite their electrically neutral composition in the comet's nucleus. Charged dust particles follow complex trajectories determined by the balance between gravitational, electromagnetic, and radiation pressure forces, creating spatial variations in dust density that influence atmospheric heating rates through absorption of solar radiation. The magnetic field strength in Mars's upper atmosphere varies dramatically with altitude, local time, and solar wind conditions, ranging from a few nanotesla in quiet regions to several hundred nanotesla near crustal magnetic anomalies. These field variations create magnetic gradients that trap charged particles in bottle-like configurations, potentially concentrating comet-derived ions in specific atmospheric regions where magnetic field strength reaches local maxima. Induced electric fields generated by atmospheric motion through magnetic field lines can accelerate ions to energies sufficient for impact ionization of neutral molecules, creating cascades of secondary ionization that enhance plasma density in regions of strong atmospheric circulation. These electric field acceleration mechanisms operate most efficiently during dust storm events when atmospheric winds reach maximum velocities. The radius of charged particles in Mars's magnetic environment determines their ability to cross magnetic field lines and reach specific atmospheric regions. Typical proton gyroradii measure several kilometers in the interplanetary magnetic field, comparable to atmospheric scale heights at 200-kilometer altitude. This coincidence means that electromagnetic effects cannot be treated as small perturbations to particle trajectories, but must be included self-consistently in models of atmospheric interaction. Whistler mode electromagnetic waves propagate through Mars's ionosphere at frequencies ranging from a few hertz to several kilohertz, carrying energy and momentum that can influence chemical reaction rates through resonant wave-particle interactions. These plasma waves exhibit dispersion characteristics that depend on electron density and magnetic field strength, creating frequency-dependent propagation velocities that determine which particle populations experience resonant acceleration. Dust devils spiral across Mars's rust-coloured plains with the patient persistence of atmospheric convection, lifting microscopic particles tens of kilometres into the thin air where they encounter descending visitors from interstellar space. The planet's surface winds, driven by solar heating and topographic channeling effects, transport terrestrial dust upward through the lower atmosphere, while celestial debris from 3I/Atlas drifts downward through the upper atmospheric layers. These opposing vertical motions create a complex three-dimensional mixing environment where materials from Mars and the outer solar system intersect. Martian dust storms range from local whirlwinds barely a meter across to planet-encircling tempests that obscure surface features for months. The dust particles themselves measure typically 1 to 10 micrometers in diameter, composed primarily of iron oxide minerals that give Mars its characteristic reddish appearance. These grains possess irregular shapes and rough surfaces that influence their aerodynamic properties and electrical charging characteristics as they move through the planet's electrified atmosphere. Electrostatic forces generated during dust particle collisions create charge separation that builds substantial electric fields within Martian dust storms. Laboratory experiments demonstrate that basaltic dust similar to that found on Mars can generate electric field strengths exceeding 100,000 volts per meter during saltation processes, where particles bounce along the surface before becoming airborne. These electric fields accelerate charged particles and influence chemical reaction rates through field emission and impact ionization mechanisms. The vertical transport of dust through Mars's atmosphere operates through several distinct mechanisms, each dominant at different altitudes and wind conditions. Convective mixing driven by surface heating can loft particles to altitudes exceeding 10 kilometers, while large-scale circulation patterns associated with seasonal atmospheric dynamics carry dust across hemispheric distances. Gravitational settling provides the opposing downward flux that eventually returns dust particles to the surface on timescales ranging from hours to months, depending on particle size and atmospheric density. Comet particles descending through Mars's upper atmosphere encounter this dusty environment at altitudes where atmospheric density begins to influence particle trajectories significantly. The collision frequency between comet debris and atmospheric constituents increases exponentially with decreasing altitude, following the atmospheric density profile that peaks near the surface. Most comet particles undergo complete vaporization above 80 kilometers altitude, though larger grains might survive to lower altitudes where dust concentrations reach maximum values. Brownian motion affects the smallest particles in both populations. Martian dust grains below 1 micrometer diameter and comet debris particles in the nanometer size range experience random walk trajectories driven by molecular collisions with atmospheric gas molecules. This stochastic motion creates diffusive mixing that operates independently of bulk atmospheric circulation, ensuring that particle populations become thoroughly mixed on timescales determined by atmospheric density and temperature profiles. The charging mechanisms affecting dust and comet particles differ due to their distinct compositional and environmental histories. Martian dust acquires charge primarily through triboelectric effects during particle-particle collisions and through photoelectric emission when exposed to solar ultraviolet radiation. Comet particles, emerging from an environment of near zero temperature and negligible electromagnetic fields, initially carry minimal electric charge but quickly equilibrate with the plasma environment of Mars's upper atmosphere. Atmospheric turbulence in Mars's boundary layer, extending from the surface to altitudes of several kilometers, creates chaotic mixing that enhances the dispersion of both dust and comet particles beyond what would result from molecular diffusion alone. Turbulent eddies with length scales ranging from meters to kilometers transport particles both horizontally and vertically with velocities that can exceed the gravitational settling speed for smaller grains. The optical properties of Martian dust influence atmospheric heating rates through absorption and scattering of solar radiation, creating thermal gradients that drive convective motion and modify particle transport patterns. Dust-laden air absorbs solar energy more efficiently than clear atmosphere, leading to enhanced heating that can trigger convective instabilities and dust devil formation. These feedback mechanisms couple atmospheric dynamics to dust loading in complex ways that remain active areas of research. Comet particles entering Mars's dusty atmosphere might serve as condensation nuclei for cloud formation if atmospheric conditions reach saturation with respect to water vapor or carbon dioxide. The heterogeneous nucleation process requires surface sites where gas molecules can adsorb and begin forming liquid or solid phases, with nucleation efficiency depending on particle composition, surface area, and chemical reactivity. Electromagnetic scattering of radio waves by charged dust particles creates plasma frequency variations detectable by radioscience experiments aboard Mars orbiters. These measurements provide remote sensing capabilities for monitoring dust storm development and intensity through changes in atmospheric electrical properties. The technique offers temporal resolution superior to visible light imaging during periods when dust obscures optical observations of surface features. Size-selective particle transport occurs when atmospheric turbulence and gravitational settling operate on comparable timescales, creating vertical sorting effects that segregate particles according to their aerodynamic properties. Smaller particles remain suspended at higher altitudes for extended periods, while larger grains settle more rapidly toward the surface. This size-dependent fractionation creates compositional gradients in the atmospheric particle population. Chemical weathering of Martian dust occurs slowly under current atmospheric conditions due to the absence of liquid water and the low concentrations of chemically reactive gases. However, trace amounts of atmospheric water vapor can catalyze oxidation reactions that modify dust particle surface chemistry over geological timescales. Comet particles might introduce exotic chemical species that accelerate these weathering processes through catalytic mechanisms. The momentum transfer between wind and particles determines the threshold wind speeds required to initiate dust lifting from Mars's surface. This threshold depends on particle size, surface roughness, and atmospheric density in ways described by semi-empirical relationships developed through laboratory experiments and field observations. The current thin atmosphere of Mars requires higher wind speeds to lift particles compared to conditions that might have existed during earlier epochs when atmospheric pressure was greater. Dust particle aggregation occurs when electrostatic or van der Waals forces overcome the kinetic energy of individual grains, leading to the formation of larger composite particles with modified aerodynamic properties. These aggregates can persist for extended periods in Mars's low-density atmosphere, where collision frequencies remain insufficient to disrupt weak interparticle bonds through mechanical impact. Seasonal variations in dust storm activity correlate with Mars's eccentric orbit, which creates asymmetric heating patterns between northern and southern hemispheres. During southern hemisphere summer, enhanced solar heating drives global-scale atmospheric circulation that can trigger planet-wide dust storms lasting for months. These seasonal patterns influence the vertical distribution of atmospheric dust at the time of 3Y/Atlas's encounter. The Goldilocks zone of contact emerges at precisely 80 kilometers altitude above Mars's rust-colored surface, where atmospheric density reaches optimal values for the gentlest possible integration between terrestrial and celestial chemistry. Too high, and molecular collision frequencies drop below levels necessary for meaningful chemical interaction. Too low, and atmospheric drag forces become sufficiently intense to vaporize comet particles through frictional heating before chemical equilibration can occur. At exactly this intermediate altitude, conditions prove just right for the most delicate atmospheric alchemy. Atmospheric pressure at 80 kilometers measures approximately 0.001 pascals, roughly 1/10,000,000th the pressure at Earth's sea level, yet still dense enough to support collision frequencies that enable gas phase chemical reactions to proceed on timescales of minutes to hours. This pressure regime represents a transition zone between the collision-dominated lower atmosphere, where fluid dynamics principles apply, and the collision-free upper atmosphere, where individual particle trajectories follow ballistic paths through the planet's gravitational field. Temperature profiles through this critical altitude region exhibit complex vertical structure determined by the balance between solar heating, radiative cooling, and atmospheric circulation. During daytime periods, solar absorption by trace atmospheric constituents creates temperature inversions where atmospheric temperature increases with altitude, establishing convective stability that suppresses vertical mixing. Nighttime radiative cooling reverses these temperature gradients, creating convective instability that enhances vertical transport of trace species. The mean free path of gas molecules at 80 kilometers altitude approaches several hundred meters, indicating that atmospheric behavior occupies an intermediate regime between continuum fluid mechanics and molecular kinetics. Individual molecules travel substantial distances between collisions, yet collision frequencies remain sufficiently high to establish local thermodynamic equilibrium on timescales much shorter than chemical reaction timescales. This kinetic regime creates unique opportunities for studying molecular collision processes under conditions intermediate between laboratory and interstellar environments. Chemical reaction networks at this altitude involve primarily three-body association reactions, where two reactant molecules require collision with a third body to remove excess energy and stabilize reaction products. The low atmospheric density limits the availability of third bodies, constraining reaction pathways to those that can proceed through radiative stabilization or direct two-body association mechanisms. These mechanistic constraints favor simple chemical transformations over complex multi-step reaction sequences. Comet particles reaching 80 kilometers altitude have survived atmospheric entry heating that vaporize smaller grains at higher altitudes, indicating compositions dominated by refractory minerals and organic compounds with high sublimation temperatures. These surviving particles typically measure between 10 nanometers and 1 micrometer in diameter, small enough to remain suspended in atmospheric turbulence for extended periods, yet large enough to serve as condensation nuclei for heterogeneous chemical processes. Atmospheric turbulence at this altitude operates in a regime dominated by buoyancy-driven convection rather than mechanical shear. creating vertical transport velocities typically measuring centimeters per second. These gentle circulation patterns provide sufficient mixing to distribute comet-derived chemistry horizontally across hundreds of kilometers while maintaining vertical residence times of days to weeks for chemically processed materials. The solar zenith angle dependence of photochemical processes creates diurnal variations in chemical reaction rates that modulate the efficiency of comet-atmosphere interaction. During local noon, when solar ultraviolet radiation reaches maximum intensity, photodissociation rates peak while gas phase temperatures reach daily maximum values. These enhanced photochemical conditions favor rapid processing of comet molecules through radical chemistry pathways. Radiative transfer calculations reveal that atmospheric opacity at 80 kilometers remains sufficiently low to permit penetration of solar ultraviolet radiation necessary for photochemical activation, yet sufficiently high to provide thermal infrared emission that moderates temperature extremes. This optical depth balance creates a photochemical environment where both solar-driven and thermally activated chemical processes can operate simultaneously. Mass spectrometric measurements from orbiting spacecraft demonstrate that atmospheric composition at 80 kilometers exhibits significant variability associated with global circulation patterns, dust storm activity, and seasonal changes in solar heating. Water vapor concentrations vary by orders of magnitude depending on atmospheric transport from polar ice caps and subsurface reservoirs, creating temporal variations in the chemical environment encountered by comet particles. The gravitational settling velocity for typical comet dust particles at 80 kilometers altitude approaches 1 meter per hour, slow enough that vertical transport by atmospheric circulation can compete effectively with gravitational precipitation. This balance between settling and mixing creates extended residence times that allow chemical equilibration to occur before particles reach lower altitudes, where higher atmospheric densities drive rapid chemical processing. Electromagnetic field effects at this altitude arise primarily from the global electric circuit, maintained by charged particle precipitation and surface charging processes rather than from planetary magnetic field interactions. These electric fields, typically measuring millivolts per meter, remain too weak to significantly influence neutral particle trajectories, but can affect the motion of charged comet debris through electrostatic acceleration mechanisms. Laboratory analog experiments conducted in rarefied gas environments provide calibration data for interpreting atmospheric chemical processes at 80 kilometers altitude, though reproducing the exact pressure, temperature, and radiation conditions present significant technical challenges. Most experimental studies operate at pressures several orders of magnitude higher than planetary atmospheric values, necessitating theoretical extrapolations based on collision theory and reaction kinetics principles. The horizontal scale length for atmospheric mixing at 80 kilometers approaches planetary dimensions, indicating that chemical traces injected at this altitude can achieve global distribution on timescales of weeks to months through atmospheric circulation. This efficient horizontal transport ensures that chemical signatures of the comet encounter spread throughout Mars's atmospheric system rather than remaining localized near the initial interaction region. Condensation nuclei concentrations at 80 kilometers typically measure fewer than 1 particle per cubic centimeter, creating nucleation-limited conditions for cloud formation processes. The injection of comet particles might temporarily enhance nucleation efficiency for atmospheric condensation. Though the extremely low water vapor concentrations characteristic of Mars's upper atmosphere severely limit cloud formation potential, even with enhanced nucleation sites. Photochemical modeling of atmospheric chemistry at 80 kilometers requires consideration of dozens of molecular species connected through hundreds of chemical reactions, each with rate coefficients that depend sensitively on temperature, pressure, and radiation field intensity. The addition of comet-derived chemistry introduces new reaction pathways that can significantly alter atmospheric chemical balance through catalytic mechanisms and radical chain reactions. Atmospheric escape processes operating at 80 km altitude include both thermal and non-thermal mechanisms that determine the ultimate fate of comet-derived materials. Light species such as hydrogen can achieve escape velocities through thermal heating, while heavier molecules require non-thermal acceleration through processes such as dissociative recombination or charge exchange with solar wind ions to escape Mars's gravitational field. Spectroscopic signatures of passage whisper through electromagnetic frequencies as ground-based telescopes detect the subtlest changes in atmospheric composition during 3 Weiss/Atlas's encounter with Mars. These optical fingerprints manifest as minute variations in absorption line depths and emission feature intensities, measurable only through the most sophisticated spectroscopic techniques developed for planetary atmospheric research. Each wavelength carries information encoded in quantum mechanical transitions between rotational and vibrational energy states of atmospheric molecules. High-resolution infrared spectrometers operating in the 2.5 to 5 micrometer wavelength range detect water, vapor absorption lines with precisions approaching parts per billion, sufficient to resolve concentration enhancements caused by sublimation of comet ice. The fundamental vibrational transitions of water molecules create distinctive absorption patterns that shift systematically with temperature and pressure, allowing spectroscopists to determine not only molecular concentrations, but also the physical conditions where these molecules reside in Mars's atmosphere. Doppler spectroscopy reveals atmospheric circulation patterns through frequency shifts in molecular absorption lines caused by bulk motion of gas masses relative to the observing telescope. Wind velocities in Mars's upper atmosphere, typically measuring tens of meters per second, produce Doppler shifts of a few parts in 10 million at optical wavelengths, detectable only through laser-stabilized spectrometers with exceptional frequency stability and calibration accuracy. Carbon monoxide molecules from 3/Atlas exhibit characteristic absorption signatures in the 2.3 micrometer spectral region, where the fundamental vibration-rotation transitions produce a series of sharp absorption lines spaced at regular frequency intervals. The relative intensities of these lines depend on the rotational temperature of the molecular population, providing information about energy distribution and collision rates in the upper atmospheric environment where comet gases interact with indigenous atmospheric constituents. Emission spectroscopy complements absorption measurements by detecting photons generated through atmospheric chemical processes rather than those absorbed during transmission through atmospheric layers. Chemiluminescent reactions involving hydroxyl radicals produce emission features in the near-infrared spectrum, while recombination of atmospheric ions generates emission lines throughout the visible and ultraviolet spectral regions. These emission processes create active signatures of chemical processing that reveal reaction rates and energy transfer mechanisms. Isotopic spectroscopy exploits the subtle frequency differences between absorption lines of different isotopic species to determine isotope ratios in atmospheric constituents. Water molecules containing deuterium rather than ordinary hydrogen exhibit absorption lines shifted by approximately 0.1% relative to normal water, detectable through ultra-high resolution spectroscopy with resolving powers exceeding 1 million. These isotopic measurements provide constraints on the origin and processing history of atmospheric water vapor. Zeeman spectroscopy utilizes the splitting of spectral lines in magnetic fields to probe electromagnetic conditions in Mars's upper atmosphere. Though the planet's weak magnetic field produces Zeeman splittings at the limit of current observational capabilities, advanced polarimetric techniques can detect magnetic field strengths as low as 1 microtesla through circular polarization measurements of specific atomic transitions, providing insights into electromagnetic processes affecting atmospheric chemistry. Temporal variations in spectroscopic signals reveal the dynamic evolution of atmospheric composition as comet materials mix with indigenous atmospheric constituents. Monitoring campaigns extending over weeks to months document the gradual dispersion and chemical processing of comet-derived molecules, providing observational data for validating atmospheric circulation models and chemical kinetics calculations. Limb-sounding spectroscopy observes atmospheric absorption along tangential paths through Mars's atmosphere, providing altitude-resolved measurements of atmospheric composition with vertical resolution approaching 1 kilometer. This geometric technique exploits the exponential decrease in atmospheric density with altitude to achieve high vertical resolution, while maintaining sufficient sensitivity to detect trace constituent concentrations in the upper atmospheric regions where comet interaction occurs. Fourier transform spectroscopy enables simultaneous measurement of thousands of spectral lines across broad wavelength ranges, providing comprehensive chemical inventories of atmospheric composition during the comet encounter. These multiplex measurements reveal correlations between different molecular species that indicate chemical reaction pathways and mixing ratios. Though the data analysis requires sophisticated statistical techniques to extract meaningful signals from complex spectral datasets, radio occultation spectroscopy utilizes signals transmitted from spacecraft behind Mars as they pass through the planet's atmosphere, providing high-precision measurements of atmospheric density, temperature, and composition profiles. The technique achieves vertical resolution better than 100 meters and can detect atmospheric perturbations caused by comet particle injection through precise monitoring of signal phase and amplitude variations. Heterodyne spectroscopy employs laser local oscillators to achieve frequency resolution approaching 1 part in 10 billion, enabling detection of atmospheric velocity fields through Doppler measurements with accuracies of a few meters per second. These precision velocity measurements reveal atmospheric circulation patterns and turbulent mixing processes that transport comet-derived chemistry throughout Mars's upper atmosphere on timescales comparable to the encounter duration. Differential absorption spectroscopy compares simultaneous measurements at wavelengths inside and outside molecular absorption lines to isolate atmospheric signals from instrumental and atmospheric background effects. This technique achieves sensitivity levels sufficient to detect column density, changes of a few % in atmospheric trace constituents, providing quantitative measurements of comet material injection rates and subsequent atmospheric processing. Laboratory spectroscopy provides reference data for interpreting planetary atmospheric observations through precise measurements of molecular transition frequencies, line strengths, and pressure broadening parameters under controlled conditions. These laboratory calibrations remain essential for converting observed spectral line intensities into molecular concentrations and for identifying previously unobserved atmospheric constituents that might result from comet atmosphere chemical interactions. Theoretical spectroscopy calculations based on quantum mechanical principles predict spectral line positions and intensities for atmospheric molecules under planetary conditions, though computational requirements limit these calculations to relatively simple molecular systems. Advanced electronic structure methods can predict spectroscopic parameters for small molecules with accuracies approaching experimental precision, while approximate methods provide estimates for larger molecular species. Long-path absorption spectroscopy conducted in ground-based laboratories simulates atmospheric optical path lengths, by employing multiple reflection cells that extend effective absorption paths to several kilometers. These experiments enable detection of weak absorption features and provide calibration data for interpreting planetary observations under conditions that approximate atmospheric pressure and temperature environments. Cavity ring-down spectroscopy achieves exceptional sensitivity for trace gas detection by measuring the exponential decay time of laser light confined within a high-finesse optical cavity. This technique can detect molecular concentrations at the parts per trillion level, though its application to planetary atmospheric observations remains limited by the requirement for precise optical alignment and vibration isolation. Photoacoustic spectroscopy detects absorbed optical energy through the acoustic waves generated by thermal expansion following molecular absorption of laser radiation. While primarily used for laboratory gas analysis, this technique might find application in future Mars atmospheric studies through instruments that detect sound waves generated by laser-induced heating of atmospheric constituents. Raman spectroscopy exploits inelastic scattering of laser light by atmospheric molecules to provide information about molecular vibrations and rotational states independent of infrared absorption properties. Though typically requiring higher molecular concentrations than available in planetary atmospheres, resonance-enhanced Raman techniques might achieve sufficient sensitivity for detecting atmospheric constituents during special conditions such as comet encounters. Correlation spectroscopy employs statistical analysis of spectral data to identify weak signals buried in noise through cross-correlation techniques that exploit the distinctive patterns of molecular absorption line systems. These methods can extract atmospheric composition information from low signal-to-noise ratio observations by comparing measured spectra with high-resolution laboratory reference spectra of candidate molecular species. Time-resolved spectroscopy monitors rapid changes in atmospheric composition on timescales of seconds to minutes, revealing transient chemical processes and atmospheric dynamics that occur during brief encounter periods. High-speed data acquisition systems enable temporal resolution sufficient to resolve chemical reaction kinetics and atmospheric mixing processes that operate on timescales comparable to molecular collision times. Hyperspectral imaging spectroscopy combines spatial and spectral information to map atmospheric composition variations across planetary hemispheres, providing context for understanding how local comet atmosphere interactions affect global atmospheric chemistry. These measurements require sophisticated data processing techniques to separate atmospheric signals from surface reflection and thermal emission contributions. Polarization spectroscopy exploits the vector properties of electromagnetic radiation to probe atmospheric structure and composition through measurements of linear and circular polarization states. Scattering by atmospheric particles and molecules modifies polarization characteristics in ways that provide information about particle size distributions, refractive indices, and magnetic field orientations in planetary atmospheres. The patience of planetary archives reveals itself through Mars's polar ice caps, where layers of frozen carbon dioxide and water ice accumulate with the measured cadence of seasonal change. Each annual deposit preserves atmospheric composition like pages in a geological book, recording trace elements and isotopic signatures that document environmental conditions during deposition. Now, as 3I/Atlas streams through Mars's upper atmosphere, these ancient repositories begin incorporating the first interstellar chemistry to reach the planet's frozen archives in recorded history. Carbon dioxide snow falls continuously at Mars's polar regions during winter months, when atmospheric temperatures drop below 148 Kelvin and permit direct condensation of the planet's primary atmospheric constituent. These microscopic crystals incorporate trace atmospheric constituents through co-condensation processes that selectively concentrate different molecular species depending on their vapor pressures and chemical affinities for ice crystal surfaces. Water vapor from 3/Atlas becomes trapped within this frozen matrix alongside indigenous atmospheric constituents. The layered structure of polar ice deposits extends downward through hundreds of meters of accumulated frozen material, representing millions of years of atmospheric deposition under varying climatic conditions. Orbital variations in Mars's axial tilt and eccentricity create cyclical changes in polar heating that modulate ice accumulation rates and preservation, producing distinctive stratigraphic patterns visible in high-resolution orbital imagery of polar scarps and exposed cliff faces. Isotopic fractionation during ice crystal formation creates compositional variations that preserve information about atmospheric temperature, pressure, and circulation patterns during deposition. Deuterium concentrations in polar ice reflect atmospheric water vapor sources and transport pathways, while carbon isotope ratios in frozen carbon dioxide record photochemical processing rates and atmospheric escape processes. The injection of comet material adds new isotopic signatures that future atmospheric scientists might detect in polar ice cores. Atmospheric circulation patterns transport materials from equatorial and temperate regions toward the polar ice caps through meridional circulation cells driven by seasonal heating asymmetries. These transport processes can carry comet-derived chemistry deposited initially in low-latitude regions toward polar accumulation zones over timescales of months to years, ensuring that signatures of the 3/Atlas encounter become incorporated into permanent geological archives. Sublimation and redeposition processes continuously modify polar ice composition as seasonal temperature changes drive phase transitions between solid and gaseous phases. During spring and summer months, solar heating sublimes surface ice layers, releasing trapped atmospheric constituents that can undergo photochemical processing before redeposition in colder regions. These seasonal cycling processes tend to concentrate refractory materials while allowing volatile constituents to escape to space. Crystal structure analysis of Martian polar ice reveals hexagonal arrangements characteristic of ordinary water ice. Though trace impurities and rapid cooling during atmospheric deposition can produce metastable phases with different crystal symmetries, the incorporation of foreign molecules such as carbon monoxide or methane from comet sources might stabilize clathrate hydrate structures that trap guest molecules within cages formed by hydrogen-bonded water frameworks. Dust layers interspersed throughout polar ice deposits record major dust storm events and seasonal variations in atmospheric dust loading, providing temporal markers that enable precise dating of ice layer sequences. The correlation between dust layer thickness and orbital records of dust storm activity demonstrates that polar ice archives preserve high-fidelity records of atmospheric dynamics extending back several million years into Mars's climatic history. Atmospheric pressure variations associated with seasonal condensation and sublimation of polar carbon dioxide create global-scale pressure oscillations that influence atmospheric circulation and trace constituent transport. During southern hemisphere winter, up to 25% of Mars's total atmospheric mass condenses at the south polar cap, significantly altering global atmospheric dynamics and chemical transport patterns. These pressure changes might influence the distribution and preservation of comet-derived materials. Trace element analysis of terrestrial polar ice provides analogous information about atmospheric composition and environmental conditions on Earth, demonstrating the potential scientific value of similar analyses conducted on Martian polar deposits. volcanic eruptions, forest fires, and anthropogenic emissions all leave distinctive chemical signatures in polar ice that can be detected decades to millennia after the original atmospheric injection events. Spectroscopic analysis of exposed polar ice layers using infrared spectrometers aboard Mars orbiters reveals compositional variations that correlate with stratigraphic boundaries and climatic transitions. Water ice exhibits characteristic absorption features near 1.5 and 2, 0 micrometers, while carbon dioxide ice shows distinctive absorption bands in the 2.0 to 2.1 micrometer region. Trace constituents produce weaker absorption features that require sophisticated spectral analysis techniques to detect and quantify. Thermal properties of polar ice deposits influence seasonal heating and cooling rates that determine sublimation and condensation patterns during annual cycles. The thermal conductivity of ice depends on temperature, crystal structure, and impurity concentrations in ways that create feedback mechanisms between atmospheric dynamics and ice cap behavior. These thermal processes might preferentially preserve or destroy chemical signatures of the comet encounter. Atmospheric escape processes preferentially remove light isotopes and volatile constituents from Mars's atmosphere, creating isotopic and compositional evolution that becomes recorded in polar ice deposits over geological time. The gradual loss of atmospheric mass through escape processes creates long-term trends in ice composition that provide constraints on atmospheric evolution models and planetary climate history. Radar sounding techniques penetrate deeply into polar ice deposits, revealing internal layer structures and thickness variations that document the history of ice accumulation and ablation. Ground-penetrating radar systems can detect compositional boundaries and structural discontinuities within ice deposits to depths exceeding 1 kilometer, providing three-dimensional views of polar ice stratigraphy and temporal variations in accumulation rates. Robotic drilling missions proposed for future Mars exploration would extract ice cores from polar deposits for detailed laboratory analysis of atmospheric composition and environmental conditions throughout Mars's recent geological history. Such missions would provide unprecedented insights into atmospheric chemistry, climate variability, and potential biosignature preservation, while also documenting any traces of the 3 I/8-less encounter preserved in frozen atmospheric archives. Future human missions to Mars might establish permanent research stations near polar regions to conduct continuous monitoring of atmospheric composition and ice accumulation processes, creating real-time records of environmental conditions analogous to Antarctic research stations on Earth. These facilities would provide invaluable data for understanding Martian climate systems and detecting future encounters with interstellar visitors. Comparative planetology studies of ice deposits on other planetary bodies throughout the solar system reveal common principles governing atmospheric ice interactions, while highlighting unique aspects of each planetary environment. Jupiter's moons, Europa and Ganymede, Saturn's moon Enceladus, and Pluto all contain substantial ice deposits that preserve records of environmental conditions, though the specific chemical and physical processes differ significantly from those operating on Mars. Orbital mechanics and ephemeral encounters unfold with the precise timing of celestial clockwork. As 3 I/8-LAS approaches its point of closest approach to Mars along a hyperbolic trajectory calculated months in advance by orbital dynamicists, the geometry of this cosmic alignment represents a singular moment in solar system history. Never again will this particular comet return along the same path. Never again will Mars occupy precisely this position in its orbit when pristine outer solar system materials stream past the planet's thin atmosphere. The closest approach occurs at 1437, universal coordinated time, on a date predetermined by gravitational dynamics and the conservation of energy and angular momentum. At this moment, 3I/Atlas passes within 800 kilometers of Mars's surface, close enough that the planet's gravitational field focuses comet particles toward the night-side hemisphere, where atmospheric densities reach their daily minimum values. This geometric alignment creates optimal conditions for gentle atmospheric interaction while minimizing heating effects that might vaporize delicate comet materials. Relative velocity between comet and planet reaches 22.7 kilometers per second during closest approach, fast enough to traverse Mars's diameter in less than 5 minutes, yet slow enough for meaningful chemical exchange between comet molecules and atmospheric constituents. This velocity represents the vector combination of 3I/Atlas's heliocentric orbital motion and Mars's own orbital velocity, modified by gravitational focusing effects that become significant only within the planet's sphere of influence. The duration of atmospheric interaction extends far beyond the brief moment of closest approach due to the extended spatial distribution of material within 3I/Atlas's coma and tail. Particles ejected from the comet nucleus days or weeks earlier follow slightly different trajectories that intersect Mars's atmosphere over a period of several days, creating a prolonged encounter that allows comprehensive study of comet-atmosphere interaction processes under varying geometric conditions. Three-body dynamics involving the Sun, Mars, and individual comet particles create complex gravitational perturbations that influence particle trajectories in subtle but measurable ways. While the Sun's gravitational field dominates the overall orbital motion of 3I/Atlas, Mars's gravitational attraction becomes locally significant for particles in the comet's immediate vicinity, producing focusing effects that concentrate certain size fractions of comet debris towards specific atmospheric regions. Angular momentum conservation requires that comet particles maintain constant aerial velocity as they traverse elliptical or hyperbolic trajectories around Mars, meaning that particles move most rapidly during closest approach and most slowly at their maximum distance from the planet. This velocity variation influences collision frequencies with atmospheric molecules and determines the time available for chemical reactions to occur at different phases of the encounter. Gravitational slingshot effects, though negligible for the comet nucleus itself due to its high velocity and Mars's small mass, can significantly alter the trajectories of smaller particles in the coma that possess lower kinetic energies. These gravitational deflections can redirect particles onto trajectories that intersect Mars's atmosphere multiple times, extending interaction durations and creating complex spatial patterns of particle deposition. Tidal forces exerted by Mars on 3I/Atlas remain far too weak to disrupt the comet's structural integrity, unlike the dramatic fragmentation events observed when comets pass extremely close to massive planets like Jupiter. The maximum tidal acceleration experienced by the comet nucleus measures less than 1 millimeter per second squared, insufficient to overcome the weak gravitational self-attraction that holds the nucleus together. Atmospheric drag forces begin affecting comet particles at altitudes near 150 kilometers, where Mars's thermosphere reaches sufficient density to produce measurable deceleration of incoming debris. Particles experiencing atmospheric drag follow spiraling trajectories that gradually lose altitude and velocity, with the specific trajectory shape determined by the balance between gravitational acceleration, atmospheric drag, and any residual velocity components perpendicular to the radial direction. The encounter geometry creates distinct phases of interaction characterized by different atmospheric conditions and particle flux intensities. During the approach phase, only the most diffuse outer envelope of the comet's coma intersects Mars's exosphere, producing subtle enhancements in atmospheric composition detectable through sensitive spectroscopic analysis. The interaction intensifies during closest approach as denser regions of the coma encounter higher atmospheric densities. Doppler shift measurements of spectral lines from atmospheric constituents reveal bulk atmospheric motion during the encounter, as gravitational perturbations and heating effects drive circulation patterns that transport comet-derived materials throughout Mars's upper atmosphere. These velocity measurements provide observational constraints for atmospheric dynamics models that predict how chemical traces disperse following injection at specific altitudes and locations. Light travel time effects become significant when coordinating observations from a multiple spacecraft and ground-based telescopes separated by interplanetary distances. Radio signals from Mars orbiters require between 4 and 24 minutes to reach Earth depending on planetary orbital positions, necessitating precise timing coordination to ensure simultaneous measurements during the brief encounter period. Kepler's laws of planetary motion govern the long-term orbital evolution of 3-1/8 as it continues its journey through the solar system following the Mars encounter. The comet's orbital period becomes infinite for its hyperbolic trajectory, meaning it will never return to the inner solar system but instead will continue outward toward interstellar space, gradually fading as solar heating diminishes and outgassing ceases. Orbital perturbations caused by gravitational interactions with Jupiter, Saturn, and other massive solar system objects accumulate over time to produce small but measurable changes in 3I/Attilus's trajectory that influence its ultimate fate. These perturbations can either increase the comet's velocity, hastening its departure from the solar system, or decrease its energy, potentially creating the possibility of eventual return after millions of years in interstellar space. Atmospheric heating effects during the encounter produce temperature perturbations that propagate through Mars's atmospheric layers as acoustic waves travelling at the local speed of sound. These pressure oscillations dissipate their energy through viscous damping and radiative cooling, though their initial amplitudes might be detectable through sensitive pressure measurements conducted by surface-based meteorological instruments. Gravitational wave emissions from the Mars comet system remain far too weak for detection by current instrumentation, though they represent a fundamental prediction of general relativity for any system involving accelerated masses. The quadrupole moment variations associated with 3I/Atlas's hyperbolic passage produce gravitational radiation with strain amplitudes, many orders of magnitude below the sensitivity thresholds of the most advanced gravitational wave detectors. Energy dissipation through atmospheric drag converts kinetic energy of comet particles into heat that raises atmospheric temperatures in localized regions where particle deposition occurs most intensively. These heating effects create buoyancy-driven convection that enhances vertical mixing and accelerates the redistribution of comet-derived chemistry throughout the atmospheric column. Solar wind and interstellar gifts converge in the electromagnetic environment surrounding Mars as charged particles streaming outward from the Sun interact with the dispersing remnants of 3I/Atlas's ancient chemistry. The solar wind, composed primarily of protons and electrons, accelerated through the Sun's corona to velocities approaching 400 kilometers per second, carries embedded magnetic fields that drape around Mars like invisible curtains, creating complex plasma physics environments where comet materials undergo electromagnetic processing. Protons in the solar wind possess kinetic energies typically measuring 1 to 2 kilo-electron volts, sufficient to ionize atmospheric molecules through direct impact and to drive chemical reactions that would not occur under thermal conditions alone. These charged particles penetrate directly into Mars's upper atmosphere, due to the planet's absent magnetosphere, creating ionospheric layers where plasma densities reach maximum values during periods of high solar wind flux. Alpha particles, comprising about 4% of solar wind mass flux, carry twice the charge and 4 times the mass of protons, creating more energetic collision events when they encounter atmospheric constituents. The nuclear composition of solar wind alpha particles reflects helium produced through nuclear fusion in the Sun's core, providing a direct sample of stellar nuclear synthesis products that interact chemically with materials from the outer solar system preserved in 3/Atlas's nucleus. Interplanetary magnetic field lines embedded in the solar wind create pathways for charged particle transport that can channel comet ions across vast distances throughout the solar system. Magnetic reconnection events occurring when oppositely directed field lines encounter each other produce explosive energy releases that accelerate particles to velocities far exceeding their thermal speeds, potentially dispersing comet chemistry throughout interplanetary space. Charge exchange reactions between solar wind protons and neutral atoms from comet outgassing create energetic neutral atoms that carry information about plasma conditions in the interaction region. These collision processes produce characteristic X-ray emissions when highly charged solar wind ions capture electrons from neutral targets, creating spectroscopic signatures detectable by X-ray telescopes that reveal the spatial distribution and chemical composition of comet materials. Electromagnetic waves generated by plasma instabilities in the solar wind propagate at frequencies ranging from millihertz to megahertz, carrying energy and momentum that influence atmospheric dynamics through wave-particle interactions. Whistler mode waves, ion cyclotron waves, and magnetosonic waves all participate in the complex electromagnetic environment where comet particles encounter Mars's ionosphere and undergo acceleration, heating, and chemical modification. Magnetic field compression occurs when the solar wind encounters obstacles such as planetary atmospheres or comet comas, creating enhanced magnetic field strengths that trap charged particles in bottle-like configurations. These magnetic bottles can accelerate particles through betatron acceleration mechanisms while providing confinement that increases collision frequencies and enhances chemical reaction rates between different ion populations. Solar energetic particle events, associated with coronal mass ejections and solar flares, periodically flood interplanetary space with high-energy protons, electrons, and heavy nuclei that can reach Mars within hours of their solar origin. During such events, particle fluxes can increase by factors of thousands above background levels, creating intense ionization environments that dramatically alter atmospheric chemistry through enhanced radiation processing. The Parker spiral configuration of interplanetary magnetic field lines, created by the rotation of the Sun combined with outward solar wind flow, determines the magnetic connectivity between different regions of the solar system. Field lines threading 3/Atlas's coma might connect magnetically to field lines intersecting Mars's atmosphere, creating direct pathways for electromagnetic communication between comet and planet across spatial separations measured in astronomical units. Pickup ion acceleration occurs when newly ionized atoms from 3/Atlas's outgassing encounter the convecting solar wind plasma and become swept up in its bulk motion. These freshly minted ions experience immediate acceleration to velocities comparable to the solar wind flow speed, creating non-thermal ion populations with distinctive velocity distributions detectable through mass spectrometric analysis of plasma composition. Magnetic pressure gradients in the solar wind can focus or defocus charged particles depending on their gyroradia and drift velocities relative to magnetic field variations. These focusing effects operate on much larger spatial scales than gravitational focusing, but can produce similar concentrations of charged comet debris in specific regions where Mars's atmosphere provides optimal conditions for neutralization and chemical processing. Cometary ions created through photoionization and electron impact processes in 3 I/Atlas's coma exhibit characteristic mass-to-charge ratios that identify their parent molecular species and provide information about comet nucleus composition. Water group ions, carbon monoxide ions, and more complex organic ions each possess distinctive signatures detectable through mass spectrometric measurements that reveal the chemical diversity of outer solar system materials. Magnetic mirror effects can trap charged particles between regions of strong and weak magnetic field, creating particle populations with enhanced residence times in specific spatial regions. Particles trapped in magnetic mirror configurations undergo repeated bouncing motions that increase their probability of encountering atmospheric molecules and participating in chemical reactions that would not occur during single-pass trajectories. Electric field acceleration and current sheets and magnetic reconnection regions can energize both solar wind particles and comet ions to keV energies, creating fast ion populations capable of deep penetration into planetary atmospheres. These accelerated particles deposit their energy through ionization and excitation processes that create secondary electron cascades and enhance chemical reaction rates in atmospheric regions far below their initial interaction altitudes. Plasma turbulence develops when different ion populations with distinct velocity distributions interact through electromagnetic forces, generating broadband electromagnetic fluctuations that can scatter particles and enhance cross-field transport. The injection of comet ions into the solar wind plasma creates such multi-species configurations that might trigger turbulent cascades affecting particle transport throughout the Mars solar-wind interaction region. Gyrosynchrotron radiation emitted by relativistic electrons spiraling in magnetic fields produces radio emissions detectable by sensitive radio telescopes. Providing remote sensing capabilities for monitoring plasma conditions in the Comet-Mars interaction region, these radio signatures can reveal magnetic field strengths, electron densities, and energy distributions in plasma regions inaccessible to direct spacecraft measurements. Solar wind charge state distributions reflect coronal temperatures and ionization conditions in the solar atmosphere, providing information about solar activity levels and space weather conditions during the comet encounter. Highly charged ions such as O circumflex 7+ and Phi circumflex 16+ indicate high-temperature coronal sources, while lower charge states suggest cooler solar wind origins that produce different chemical processing environments. Atmospheric sputtering by solar wind particles gradually erodes Mars's atmospheric envelope through momentum transfer processes that eject atmospheric atoms and molecules to escape velocity. The temporary enhancement of atmospheric density by comet material injection might slightly increase sputtering yields, contributing additional atmospheric loss that compounds the long-term atmospheric evolution driven by solar wind erosion processes. The weight of cosmic visitors measures in mere nanograms distributed across millions of cubic kilometers of Martian atmosphere, creating density enhancements so subtle that detecting their presence requires the most sophisticated analytical techniques developed for planetary atmospheric science. Scientists calculate that the total mass of material from 3/Atlas intercepted by Mars's atmosphere amounts to perhaps 10 kilograms less than a typical terrestrial meteorite, yet spread throughout atmospheric volumes large enough to encompass entire terrestrial continents. Mass flux calculations based on comet outgassing rates and geometric cross-sections reveal that Mars intercepts approximately 1 part in 10 million of 3 Y/Atlas's total gas production, a fraction determined by solid angle geometry and the inverse square law governing particle dispersion in three-dimensional space. This infinitesimal sampling fraction means that even modest comets produce barely detectable atmospheric perturbations when they pass near planets, explaining why such encounters have rarely been observed despite their probable frequency throughout solar system history. Individual water molecules from the comet possess masses of approximately 3 petator, 26 kilograms, meaning that each cubic meter of enhanced atmosphere might contain at most a few million additional molecules, a concentration increase barely exceeding instrumental detection limits even with the most sensitive atmospheric monitoring systems. These minute enhancements require statistical analysis of large datasets to distinguish genuine signals from random fluctuations in atmospheric composition measurements. Atmospheric residence times for comet-derived molecules depend on altitude-dependent chemical and dynamical processes that determine how long foreign materials persist before undergoing chemical transformation or physical removal. At 150-kilometer altitude, typical residence times measure days to weeks for chemically stable molecules, while reactive species such as hydroxyl radicals undergo transformation within hours through photochemical and ion molecule reaction pathways. Gravitational settling velocities for comet dust particles depend on particle size and atmospheric density according to Stokes's law, though the extremely rarefied conditions in Mars's upper atmosphere place most particles in the molecular drag regime where continuum fluid mechanics approximations become invalid. Nanometer-sized particles settle at velocities measuring millimeters per hour, so slowly that atmospheric circulation easily overwhelms gravitational precipitation. The detection threshold for atmospheric composition measurements aboard Mars orbiters typically requires concentration enhancements exceeding 1% above background levels for definitive identification, while the most optimistic estimates for comet material injection suggest maximum enhancements of a few tenths of a percent in localized atmospheric regions. This sensitivity limitation means that confirming the atmospheric signature of 3 Wi/Atlas requires sophisticated signal processing and statistical analysis techniques. Isotopic dilution effects occur when comet materials with distinctive isotopic signatures mix with much larger reservoirs of atmospheric constituents possessing different isotope ratios. The detection of isotopic anomalies requires that comet contributions exceed approximately 10% of background atmospheric concentrations, a threshold that may never be achieved even during the most favorable encounter geometries and atmospheric conditions. Mass spectrometric measurements provide the highest sensitivity for detecting trace atmospheric constituents, with some instruments capable of identifying individual ionic species at concentration levels of parts per trillion. However, achieving such sensitivity requires careful calibration, contamination control, and background subtraction that become increasingly challenging when searching for subtle enhancements rather than completely new atmospheric constituents. Photochemical processing rates determine how rapidly comet molecules undergo chemical transformation after injection into Mars's atmosphere. With typical timescales ranging from minutes for highly reactive radicals to months for stable molecules such as carbon monoxide, these processing rates establish upper limits on the duration of detectable atmospheric signatures. As chemical transformation gradually converts distinctive comet molecules into indistinguishable atmospheric constituents, atmospheric escape processes preferentially remove light molecules such as hydrogen and helium from planetary atmospheres through thermal and non-thermal mechanisms. potentially eliminating the most distinctive signatures of comet chemistry before they can be detected or studied. Escape timescales for hydrogen atoms measure days to weeks in Mars's upper atmosphere, comparable to encounter duration and atmospheric mixing timescales. Background variability in Mars's atmospheric composition creates noise levels that obscure subtle signals associated with comet material injection. As seasonal changes, dust storm activity, and solar cycle variations produce atmospheric composition fluctuations that can exceed the magnitude of comet-induced enhancements. See, sir. Distinguishing comet signals requires careful temporal correlation with the known encounter timeline and comparison with atmospheric models that predict natural variability. Spatial distribution patterns for comet materials in Mars's atmosphere depend on injection altitude, atmospheric circulation, and particle settling velocities in ways that create highly heterogeneous concentration fields rather than uniform enhancements throughout the atmospheric volume. These spatial variations mean that detecting comet signatures might require observations at specific locations and altitudes where concentration enhancements achieve maximum values. Laboratory calibration experiments provide essential reference data for interpreting atmospheric measurements, though reproducing the exact pressure, temperature, and composition conditions characteristic of Mars's upper atmosphere presents significant technical challenges. Most laboratory studies operate under conditions that differ substantially from planetary environments, requiring theoretical extrapolations that introduce uncertainties in quantitative analysis. Temporal evolution models predict how comet material concentrations change following initial injection, incorporating atmospheric circulation, chemical processing, and escape processes through coupled differential equations that describe mass conservation for individual chemical species. These models provide frameworks for interpreting observational data and optimizing measurement strategies to maximize detection probability. Cross-contamination between different measurement techniques can produce false signals that mimic comet material signatures as instrumental backgrounds, spacecraft outgassing, and solar wind particle impacts all contribute trace constituents to atmospheric measurements. Careful intercomparison between independent measurement techniques provides essential validation for claimed detections of exotic atmospheric chemistry. Statistical significance requirements for claiming detection of comet materials typically demand signal-to-noise ratios exceeding 5 standard deviations above background levels, accounting for both measurement uncertainty and natural atmospheric variability. Meeting these stringent criteria requires either extremely sensitive instruments or fortuitous encounter conditions that produce larger than expected atmospheric perturbations. Future technological developments in atmospheric measurement techniques might enable detection of comet encounter signatures that remain below current detection thresholds. As advances in laser spectroscopy, mass spectrometry, and data analysis methods continue to improve sensitivity and reduce background interference, next-generation planetary missions might carry instruments specifically designed for detecting transient atmospheric phenomena associated with comet encounters. Comparative studies of similar encounters at other planets provide context for interpreting Mars observations. Though the unique atmospheric composition, pressure, and electromagnetic environment of each planet create distinct interaction conditions that limit direct comparability. Earth-based observations of comet passages through terrestrial upper atmosphere layers offer the most relevant analog data for understanding Mars encounter dynamics. Atmospheric memory and timescales reveal themselves through the gradual dispersion and chemical evolution of 3 I/Atlas materials within Mars's thin gaseous envelope, as molecular tracers preserve signatures of the encounter for months after the comet continues its hyperbolic journey toward interstellar space. The planet's atmosphere operates as a vast chemical reactor, where exotic outer solar system molecules mix with indigenous constituents through processes that unfold across temporal scales, ranging from microseconds for individual molecular collisions to seasons for global circulation patterns. Chemical residence times for different molecular species vary dramatically depending on their reactivity toward atmospheric constituents and their susceptibility to photochemical destruction by solar ultraviolet radiation. Water molecules from the comet survive for weeks in the Mars's upper atmosphere before undergoing photodissociation or reacting with atmospheric oxidants, while carbon monoxide exhibits much greater stability and might persist for months in regions shielded from direct solar illumination. Atmospheric circulation timescales determine how rapidly comet materials disperse from their initial injection regions to achieve global distribution throughout Mars's atmospheric system. Meridional circulation, driven by seasonal heating asymmetries, transports atmospheric constituents between hemispheres on timescales of months, while zonal circulation patterns complete circumnavigation of the planet within days to weeks depending on altitude and latitude. Isotopic equilibration between comet materials and atmospheric reservoirs occurs through chemical exchange reactions that gradually homogenize isotope ratios while preserving total element abundances. The approach to isotopic equilibrium follows exponential kinetics with characteristic timescales determined by reaction rate coefficients and molecular concentrations, typically requiring months to years for complete equilibration in Mars's low-density atmosphere. Seasonal atmospheric pressure variations associated with carbon dioxide condensation and sublimation at polar regions create systematic changes in atmospheric density that modulate chemical reaction rates and transport processes. During periods of low atmospheric pressure, reduced collision frequencies slow chemical processing, while enhanced vertical mixing accelerates the redistribution of trace constituents, including comet-derived molecules. Photochemical memory effects arise when comet materials participate in catalytic reaction cycles that continue producing distinctive chemical signatures long after the original comet molecules have undergone transformation. Hydroxyl radicals generated through water photodissociation can initiate chain reactions involving atmospheric oxygen and carbon species that create persistent chemical anomalies detectable for months through sensitive spectroscopic analysis. Temperature-dependent reaction kinetics create seasonal variations in chemical processing rates that influence how long comet material signatures persist in Mars's atmosphere. Winter cooling slows most gas phase chemical reactions exponentially according to Arrhenius behavior, while summer heating accelerates reaction rates and reduces atmospheric chemical memory through enhanced molecular collision frequencies. Gravitational wave analog effects in atmospheric density propagate information about the comet encounter throughout Mars's atmospheric system at acoustic velocities, creating pressure perturbations that can influence atmospheric circulation patterns and chemical mixing processes. These acoustic signals dissipate their energy through viscous damping on timescales of hours to days, much shorter than the months-long chemical memory of the encounter. Atmospheric escape processes continuously remove comet materials from Mars's upper atmosphere through thermal, photochemical, and ion pickup mechanisms that operate on timescales comparable to chemical residence times. Light elements such as hydrogen escape most rapidly, while heavier molecular species can achieve global atmospheric distribution before undergoing escape or chemical transformation processes. Long-term climate variability associated with Mars's orbital cycles influences atmospheric density, composition, and circulation patterns that determine how encounter signatures evolve over extended periods. Obliquity variations with periods of approximately 120,000 years modulate polar heating and atmospheric pressure in ways that might preserve or erase chemical signatures of ancient comet encounters in ice core records. Dust storm activity creates episodic perturbations to atmospheric circulation and chemistry that can either enhance or suppress the detectability of comet material signatures depending on timing and spatial distribution. Major dust storms inject large quantities of surface material into the upper atmosphere, where it interacts with comet molecules through heterogeneous chemical processes on particle surfaces. Atmospheric turbulence operating on scales from meters to hundreds of kilometers creates chaotic mixing that accelerates chemical homogenization while generating intermittent regions of enhanced or depleted comet material concentrations. Turbulent cascades transport chemical traces across multiple spatial scales, creating complex concentration patterns that evolve on timescales determined by atmospheric energy dissipation rates. Solar activity variations influence atmospheric ionization rates, escape processes, and photochemical reaction networks in ways that modulate the persistence and chemical evolution of comet materials. Solar minimum conditions favor preservation of comet signatures through reduced photodissociation rates, while solar maximum conditions accelerate chemical processing and atmospheric escape that eliminate comet traces more rapidly. Atmospheric chemistry network models incorporating hundreds of chemical reactions and dozens of molecular species predict the temporal evolution of comet material signatures under varying environmental conditions. These computational models provide frameworks for interpreting observational data and identifying optimal measurement strategies for detecting persistent chemical anomalies months after initial injection. Global circulation models, coupled with atmospheric chemistry calculations, simulate the three-dimensional transport and chemical processing of comet materials throughout Mars's atmospheric system, revealing complex spatial and temporal patterns that depend sensitively on injection altitude, atmospheric stability, and chemical reactivity parameters. These models predict where and when comet signatures achieve maximum detectability. Cross-correlation analysis techniques applied to long-term atmospheric monitoring datasets can identify subtle periodic or quasi-periodic signals associated with comet material processing, even when individual measurements lack sufficient sensitivity to detect comet signatures above instrumental noise levels. These statistical methods exploit temporal coherence to extract weak signals from large datasets spanning months to years. Atmospheric tides driven by solar heating create systematic diurnal and semi-diurnal oscillations in temperature, pressure, and composition that transport chemical traces vertically and horizontally throughout Mars's atmosphere. These tidal motions operate with precise temporal periodicity that can be predicted accurately, providing reference frames for identifying anomalous chemical transport associated with comet material dispersion. Laboratory simulation experiments conducted in low-pressure chambers with controlled temperature and radiation conditions provide insights into chemical reaction pathways and kinetics relevant to comet material processing in Mars's atmosphere. These studies reveal mechanisms by which exotic chemistry can persist or transform under planetary atmospheric conditions, informing interpretation of observational data. Future atmospheric monitoring missions equipped with enhanced sensitivity instruments and longer operational lifetimes will provide unprecedented capabilities for documenting the extended chemical evolution of comet encounter signatures, potentially revealing atmospheric memory effects that persist for years after initial material injection through complex chemical and physical processes. Return to the Void beckons. 3I/Atlas as the comet completes its singular passage through the inner solar system. leaving behind only the faintest molecular whispers of its ancient chemistry within Mars's tenuous atmosphere. The hyperbolic trajectory that carried this visitor from beyond Neptune's realm now guides it inexorably toward interstellar space, following gravitational pathways that ensure it will never retrace its steps through the planetary neighborhoods it has briefly illuminated with primordial ice and dust. Solar heating diminishes exponentially as the comet recedes from perihelion, reducing sublimation rates and gradually silencing the outgassing processes that created its spectacular tail during closest approach to the Sun. The production of water vapor, carbon monoxide, and other volatile species drops below detectable levels as surface temperatures fall toward the deep cold of interplanetary space. What remains of Theia/Atlas's nucleus will preserve its remaining ancient ices in frozen dormancy for millions of years, until chance encounters with other stellar systems might briefly reawaken sublimation processes. The comet's tail, once extending millions of kilometers behind the nucleus in gossamer streams of liberated molecules and microscopic dust, begins to dissipate as solar radiation pressure weakens with increasing heliocentric distance. Individual particles in the tail follow their own ballistic trajectories determined by their size, composition, and the radiation forces that accelerated them away from the nucleus during peak activity. The largest dust grains continue along nearly straight paths that will carry them at the outer solar system, while smaller particles spiral outward under the persistent influence of solar photons. Mars rotates in its ancient rhythm, carrying within its atmosphere the diluted chemistry of 3Wu/Atlas, distributed through global circulation patterns that will continue mixing and processing these exotic molecules for months to come. Hydroxyl radicals generated through photodissociation of comet water molecules participate in catalytic cycles that influence atmospheric oxygen chemistry, while carbon monoxide from sublimated comet ice joins the trace constituent inventory that future atmospheric monitoring missions might detect through sensitive spectroscopic analysis. Gravitational mechanics ensure that Theia/Atlas will never return along its current trajectory, though perturbations by distant stellar encounters might eventually redirect its path back toward the solar system after millions of years wandering through interstellar space. The comet carries with it a chemical archive of conditions in the outer solar nebula during planetary formation, preserving isotopic ratios and molecular structures that record temperatures and chemical processes from the solar system's violent youth. The encounter represents a natural experiment in planetary atmospheric science that provides insights into processes that shaped atmospheric evolution throughout the solar system's history. During the late heavy bombardment epoch 4 billion years ago, similar encounters occurred much more frequently as the giant planet scattered comets and asteroids throughout the inner solar system, delivering water, organic compounds, and other volatile materials that influenced early atmospheric and surface chemistry on terrestrial planets. Scientific instruments aboard Mars orbiters continue monitoring atmospheric composition for subtle signatures of the encounter. Though most comet-derived molecules will undergo chemical transformation or atmospheric escape before achieving concentrations sufficient for definitive detection, the isotopic signatures of comet ice might persist longer than individual molecules, creating anomalies in deuterium to hydrogen ratios that could remain detectable for years in atmospheric water vapor or polar ice deposits. Interstellar space awaits Theia/Atlas beyond the heliopause, where solar wind pressure balances interstellar medium density, marking the boundary between solar and galactic environments. The comet will join billions of similar objects drifting through the galaxy's spiral arms, occasionally perturbed by stellar encounters or galactic tidal forces that might redirect their trajectories toward other planetary systems. These wandering repositories of primordial chemistry serve as messengers between stellar neighborhoods, carrying samples of their formation environments across interstellar distances measured in parsecs. Computer models of the encounter provide theoretical frameworks for understanding atmospheric interactions that occurred during this brief cosmic alignment, predicting chemical reaction networks and transport processes that determine how comet materials integrate with planetary atmospheric systems. These models guide future observational strategies and instrument development programs designed to detect similar encounters around Mars and other planets throughout the solar system. The ephemeral nature of the encounter emphasizes the rarity and scientific value of direct observations of comet atmosphere interactions, as most such events throughout solar system history occurred without technological witnesses capable of documenting their chemical and physical details. Modern instrumental capabilities enable unprecedented study of processes that shaped planetary evolution during epochs when impact and encounter rates far exceeded current values. Comparative planetology studies will place the 3A/Aetolus encounter in context with similar interactions observed at other planets, revealing universal principles governing how cometary materials interact with diverse atmospheric environments. Venus's thick, hot atmosphere processes comet materials very differently than Mars's thin, cold envelope, while the giant planets create electromagnetic and gravitational environments that produce entirely distinct interaction phenomena. Archive datasets from the encounter will provide reference information for interpreting observations of comet interactions around exoplanets, where similar atmospheric processing might contribute to the chemical evolution of planetary atmospheres orbiting other stars. Spectroscopic detection of atmospheric composition changes in exoplanetary systems could reveal comet encounter events occurring in distant stellar neighborhoods. Future comet missions might carry instruments specifically designed to study atmospheric interactions when these wandering ice repositories pass near planets, providing in situ measurements of chemical and physical processes that complement remote observations from ground-based telescopes and orbiting spacecraft. Such missions could reveal how frequently planets throughout the solar system experience encounters with interstellar visitors. The cosmic perspective of the encounter places this singular event within the broader context of galactic chemical evolution. As materials formed in stellar nucleosynthesis, processes billions of years ago continue their journey through space and time, occasionally intersecting with planetary atmospheres where they contribute to the ongoing chemical evolution of worlds that might harbour or develop life. Long-term monitoring of Mars's atmospheric composition will document how signatures of the encounter fade through chemical processing, atmospheric escape, and dilution, providing observational data for validating theoretical models of atmospheric chemical evolution. These measurements contribute to understanding how planets maintain or lose their atmospheric inventories over geological timescales through interactions with interplanetary and interstellar environments. Educational and public outreach programs inspired by the encounter demonstrate how rare astronomical events can illuminate fundamental scientific principles governing planetary atmospheres, chemical evolution, and the connections between stellar and planetary environments. The encounter serves as a natural laboratory for studying processes that operate throughout the universe wherever comets interact with planetary atmospheres. The journey continues as 3I/Atlas fades into the darkness beyond Mars's orbit, carrying its ancient cargo toward destinations unknown, while Mars preserves within its thin atmosphere a molecular memory of this singular encounter between worlds separated by billions of years and astronomical distances. The red planet breathes quietly now in the aftermath of encounter, its thin atmosphere settling back into familiar patterns as the last traces of 3I/Atlas fade beyond detection range of even the most sensitive instruments. Molecules that travelled for eons through the cold darkness between worlds have found temporary residence in Mars's gossamer envelope, mixing their ancient chemistry with atmospheric constituents that record 4 billion years of planetary evolution. In the upper atmospheric layers where this cosmic alchemy occurred, temperatures continue their eternal dance between solar heating and radiative cooling, while gentle winds redistribute the diluted remnants of interstellar chemistry across hemispheric distances. The hydroxyl radicals born from comet water molecules participate quietly in photochemical networks, their signatures gradually fading as chemical equilibration erases the distinctive isotopic fingerprints that marked their extraterrestrial origin. Mars continues its elliptical journey around the Sun with the measured patience that characterizes all planetary motion, carrying within its atmospheric archive a molecular record of this singular encounter. The polar ice caps accumulate their seasonal layers of frozen carbon dioxide and water vapor, potentially preserving trace quantities of comet-derived chemistry in geological records that future explorers might someday extract and analyze. Deep space welcomes 3I/Atlas back into its ancient embrace as the comet recedes beyond the orbit of Jupiter, beyond Saturn's magnificent rings, beyond the realm where solar heating drives sublimation from its primordial surface. The nucleus carries with it the remainder of its chemical heritage from the solar system's formation epoch, preserved once again in the profound cold that has maintained these molecular structures across geological ages. 1